Okay, so in this lesson 3.4, we are going to talk about a different setup for linear equations and graphing. In particular, one that deals less with the whole function relationship. So up until now, we've been talking about input, output, domain and range, dependent, independent relationships. And a lot of times that's perfectly, helpful and exactly what we need. But the reality is that there are times where we have two quantities or two variables that form a linear relationship, but don't necessarily depend on one another. There's not really a defined dependent, independent relationship or necessarily an input-output type of thing. You're going to notice that these are going to come up in this particular situation, and when that happens, standard form a lot of times is a more natural way of setting up that equation. So today we're really focused on graphing linear equations in standard form. So we want to talk about what that means. Standard form is another way of writing the equation of a line. It's actually the official sort of, standard official way. It's not necessarily our favorite. We already talked about that. Probably still our favorite go-to is that y equals mx plus b, that slope-intercept form, because it is so informative. It gives us some really good important points. Not points, but characteristics that let us graph quickly. Standard forms looks like this. It's basically when the x term and the y term are together on one side of the equal sign, and any constants, right? Anything that doesn't have a variable, is just a number, is on the right side. Okay, so this is what standard form looks like. ax plus by equals c. Okay, that's the official. And that's standard form for a linear equation in two variables where a, b, and c are real numbers and both a and b are not zero. So one can be zero. I could have this and it's technically still standard form. We could have this right here and it's still technically standard form in a linear, but it's not, we can't be missing both because then we don't have any variable at all. Okay. And so let's talk about some examples. Once we start talking about standard form, one of the things that I want to emphasize, and this will trickle into quadratics later, is that when we're in standard form, there's standard form, but there's also like properly stated, right, proper format of a standard. So we like to define proper format as making sure that a, b, and c are integers, so there's no fractions or decimals, that a is positive, and that they don't have any common factors among themselves. Okay, so if there's something that if these were all even numbers and I could divide through by a 2, I would want to do that, for example. So here's a few examples of proper format versus not, improper format. And it's really this, all about having whole numbers, positive or negative integers, I should say, as the three coefficients. There's no common factor between those a, b's, and c's. And then this first one is positive. So these are all good examples of proper format. This is not in proper format because we have a fraction here, right? So we want to make sure that they're positive and negative integers, but no decimals or fractions. So this right here, we would want to multiply through by a 2 here to get rid of that half, okay? Same here. This is not in proper format because a is negative. The coefficient, a is the coefficient in front of x. Okay, it's whatever's attached to x here at the very, very front. And we want to make sure that's a positive whole number. So that's negative there. We would want to fix that. That's what makes this setup improper. And then very similar to this one here, this is not proper format because there's a decimal. Okay, so these are examples of what we would want it to look like. And we're going to really hone in and just focus more on that when we start writing equations. Today our main focus is going to be seeing what kind of real life situations call for standard form and what are its benefits. It does have some benefits. It might not be our favorite, but it definitely has some benefit when it comes to graphing. So I'll get to, we'll get to play off of those advantages. All right, so here's the whole thing in a nutshell. Why would we use this particular form? Well, standard form is useful when you have an equation that does not have specifically an independent-dependent relationship. So examples of this would include situations where you're deciding between two options for transportation, or your distribution tickets cost two different amounts, the seating arrangement with two table sizes. So there are a lot of situations that call for two variables. Like maybe I'm ordering tea and I'm ordering lemonade, right? Anything like that, where not necessarily one is dependent on the other. They're just two different kinds of things. So like before, we were talking about snowfall that has fallen over time. So of course, how much snow has fallen depends on how long it's been snowing. That's very clearly a dependent situation, time and how much you earn, right? How much I make depends on how many hours I work. So those are clear dependent situations. Slope intercept would be really helpful. But here, if I'm comparing between, cakes and ice cream or lemonade versus tea, that one really doesn't depend on the other. It's just more like you're comparing two different options or two different choices. And those are the situations that really lend themselves to this standard form style of equation. Okay, so let's put that into action so you can see it, because this one really is focused a lot on where does it come up in the real world. So here's a real life situation. It says here you sold $32 worth of tickets for a fundraiser. The adult tickets cost $4 a piece, and the student tickets cost $2. So you sold $32 worth. Some were $4 for the adults, $2 for the children's tickets. You lost track of how many of each ticket you sold when you're trying to figure out what are the possible combinations. Okay, so let's set up our equation. What we know is that however many adult tickets you sold, they were $4 each. Okay, so if you only did 2 of these, that's $8. If you did 3 of this, that's $12, right? So I'm doing 4 times the number of tickets, adult tickets that we sold, because those are $4 each. Plus, we also sold some student tickets. Well, those are $2 each. So $2 times however many of those you sold. But all together, that it totaled $32. Okay? So this would be our setup here. We'd be like, well, we sold some of them were $4, some of them were $2, and altogether the total was $32. Okay? So if we use X to represent this quantity right here, number of adults, tickets sold, I could really rewrite that as just, okay, well, that's going to be 4X. However many of those I sold, it's going to be times 4 to figure out how much that money that is worth. Okay? And if I use Y for the number of student tickets, I know those were $2. So now I've got 4X plus 2Y. Okay? And I know that when I tally all that up, it ended up being a total of $32. So there is a really textbook case scenario for equation that would lend itself to standard form more so than slope intercept. And it's got that X term plus the Y term together on one side, but all of that is adding up to some grand total. Okay, so that would be our equation. 4X plus 2Y equals 32. Then we can complete the table and plot the points. Okay, so we can look at different options here. And they started one for us. They basically said, what if you sold no adult tickets at all? Like 0 adult tickets, because that's what X represents, right? Then how many children's tickets would you have, or student tickets would you have sold if you made $32? So if I solve just this, divide by 2 on both sides, 32 divided by 2 is 16. That's where they got that. 2 times 16 is 32. All right, well, let's see what if we sold 1 adult ticket? Well, that would have been $4. So if I subtract that from the 32, that leaves $28. And then these being $2 each at 28, that means I would have had to sell 15 of those student tickets. If I sell 2 adult tickets, 2 times 4 is 8. So 2 adult tickets, that's $8 there. I subtract the 8. 32 minus 8, what does that give us? 24. And then 24 divided by 2. That means I would have then sold 12 student tickets. And you can start to see the pattern forming. We'll do one more. 3 adult tickets, that would have added up to $12. So I would subtract that from the total. That'd leave me $20. If I divide that by 2, that means I would have sold 10 student tickets. So I'm seeing that as X increases by 1 adult ticket, this decreases by 2 student tickets, which makes sense because it's half the price. we could kind of follow that pattern. We'll check probably one more time just to be sure. And then this would be 2. And then according to this, if I buy 8 adult tickets, so if I do 8 times 4 is 32, that would already be 32. So then that wouldn't leave me any money. I would not have been able to have sold any student tickets. So that definitely fits our data. Okay, so I just basically plugged in a few. You could plug them all in. You can start to see the pattern in the table. I checked the last one, and it sure does work. If I sold no student tickets, then 4 times 8 is how I would get 32. So then I would have had to have sold 8 adult tickets. So let's go ahead and graph this. On the X, we put number of adult tickets. So this is adult. Always label your axes. So number of adult tickets. And then on the Y is the student tickets. Okay, and then we can plot our points. And then, so basically the y-intercept here is at 16, which is way up there. And then 1 and 14, 2 and 12, 3 and 10, 4 and 8, 5 and 6, 6 and 4, 7 and 2, and then 8, 0. So there it is. Should I connect? Is number of tickets something that that is continuous or discrete? Well, it's discrete, so I would not want to connect those points. Okay. Describe the pattern formed by the points. So here's the deal, though. Even though I'm not connecting them, those points are clearly on a straight line. There it is. So we would describe that as a linear. The points form a linear pattern. Okay, and then interpret the intercept. So that's this right here. That's our y-intercept. That's this point up here on the graph. And then this is our x-intercept all the way down here. So this is important. Interpret, remember, we talked about this. It means really explain the meaning. So we've got one intercept here at 0, 16, if I thought of that as an ordered pair. So that basically means that the most you can sell is 16 student tickets if you sell no adult tickets. So this would mean the most student tickets you can sell is 16 if you don't sell any adult. Okay, that's the y-intercept. So that's what that y-intercept represents. Basically, if I sold no adult tickets, I could sell a maximum, I would have sold a maximum of 16 student tickets. And then this intercept, 0,8, so I'm going to mark this, so 8, 0, I apologize, is the other way around. Basically, you can sell up to 8 adult tickets if we don't sell any student tickets. So you sold up to 8 adult tickets if you didn't or don't, gotta get my tenses right, if you don't sell any student tickets. Okay, so that's the important part, is really being able to explain what that means. It's basically the most of one of the variables that you can sell or have if you have none of the other. And I'm going to be really clear. That is what I'll be looking for on any learning check test, whatever it is, that you can explain to me, this is the maximum that I can do of one thing if I do none of the other item. That is the meaning of those intercepts in these kinds of problems. Okay, all right, let's flip that over. Let's try another one. So it says you're planning on purchasing sandwiches for a family reunion. The large turkey subs are $5 each, and the small veggie sandwiches are $4 each. Okay. You have a total of $60 that you can spend on sandwiches. So first, we're going to write an equation to model the situation. We're going to make X the number of large sandwiches. So this is large sandwiches. And then Y is going to be the number of small sandwiches. So that's going to go along here. Okay, let's talk about what that equation looked like. Well, the large turkey ones are $5 each, so those are the X's, so that's 5X, however many I buy of that. And then the small veggie ones are $4 each, so 4Y, however many I buy. But together, I have a budget of $60, so that's got to be my total, right? So I'm going to buy some that are $5, the large ones, some that are $4, and altogether, it's going to be a $60 total. So I want to think about, this is going to allow me to kind of explore what options I have as far as purchasing those so that I can afford them. Okay, and I just paused the video and was able to play it again without having to make another video. So I just wanted to share that success story with you. Yeah, there you go. I've learned how to pause and unpause without stopping it and then having to make a second video. Yay! Okay, so let's finish this one up. So there's our equation. Basically, however many of these we buy is $5. However many of these buys we buy $4. The total has to be $60. So let's see what our options are. So what are possible combinations for the two sizes? Let's say we don't buy, let's start it simple. Let's say we don't buy any large turkey subs. Everybody wants vegetarian. Let's do it. So if we plug in a 0, this goes away. 4 times what gives us 60? Well, that's 15. Okay. So we got $15 of the veggie subs that we could afford there. And let's go ahead and plot that. So that's a y-intercept right up here. Okay, so we got a y-intercept at 15. And then let's come up with a couple of other options. Now, here it doesn't make sense. We're not going to be able to buy a half a sub or that kind of thing. So we might need to jump a little bit till the very next one, which I think is probably going to go in increments of 4. And I know that just because I've already been plotting. You could definitely plug in 1 or 2, but what you're going to find is probably you're going to get some decimals. And we know we can't buy a decimal of a sandwich. So if we shoot for 4 here, let's say we plug in a 4. 4 times 5 is 20. And that would be, okay, that means we're spending $20 on turkey subs. That would leave us 40 left. If these are $4, I could afford 10 of them. Okay? If I buy 8 of these, 8 times 5 is 40 bucks. That would cost me $40 here. That would leave me $20 left over. At 4 bucks each, I could afford 5. Okay? I could all of a sudden decide that I'm going to buy 12 of these. 5 times 12 is 60. That would take up my whole budget. If I bought 12 of these turkey large subs, then my entire $60 would go to that, and I would not have any money for any veggie options. Okay? And so let's go ahead and plot those. We've got one intercept at 15. The other intercept is down here at 12. That's the most large sandwiches if I don't buy any of the veggie. And then we will plot a couple. So it basically, if X was 4, this goes up to 10. And if this is 8, this goes up to 5. Okay, so these are probably, everything else might probably end up being a decimal. This gives us a good idea of some of the different options that we have for this particular situation. And we're just plugging in some values that we know are going to give us nice whole number sandwiches. Okay, so graph the equation, check, and interpret the intercept. So there we go. Our intercepts is where it crosses the axis. It is where the other variable is 0. Okay, and graphing it, for the first intercept, the y-intercept here is 15. And again, that is the number of veggie sandwiches you can buy, or the most. So the most veggie sandwiches you can buy if you don't buy any large turkey or any turkey sandwiches. Okay, so that's the first y-intercept. The other y-intercept, the x-intercept, happens to be 12, and did I do that right? Yes, the number of veggie sandwiches. Okay, yeah. So this is the most large turkey sandwiches you can buy if you don't buy any veggie. Sandwiches. Yeah? So that's the meaning of this intercept and that. The intercepts are always where it crosses the x and y axis. The opposite coordinate is always 0. So if you're on the y-axis, x is 0, and that's your y coordinate. If you're on the x-axis, y is 0, and that's your x coordinate. Okay, so there's our interpretation, which really brings us to when this is really useful. Believe it or not, even though standard is not our favorite necessarily, it definitely has a really nice advantage for graphing, and that is the fact that we can find those intercepts really easily from standard form, and it helps us whip up a really quick, easy graph. Okay. So this is a good thing. Pay attention to this section because it really does help a lot. So using intercepts to graph. So the advantage is that when you're in standard, you can find the intercepts really easily, the x and y intercepts. And when you have the x and y intercepts, you can graph really easily. Okay, so when your equation is written in standard form, you can easily be graphed by finding the x and y intercept. Okay, the x-intercept, ding, 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 ding. Go ahead and write that down. The x-intercept of a graph is the x-coordinate where the graph crosses the x-axis, and it always occurs, and this is important, when y is equal to 0. You're about to find out why that makes it really easy to use or easy to solve. Okay, the y-intercept, you already know this guy as being the b in the mx plus b, but it has its other advantages. So the y-intercept of the graph is the y-coordinate of a point where the graph crosses the y-axis up here. It occurs when x is equal to 0. Okay, so this is the x-intercept where it crosses the x-axis, and the opposite coordinate is always 0 there. And then this is the y-intercept where it crosses the y-axis, and the opposite coordinate is 0. Okay, so this is kind of the nifty part. So the y-intercept is found by simply solving it when x is 0. Well, here's the go. I call this the finger trick because it's pretty nice. I'm actually use this equation as an example. If I wanted to find the y-intercept super quick, guys, here's the moral of the story. The y-intercept is the y value here when that is 0. So remember, the opposite's always going to be 0. But here's the thing. When I plug in a 0 here, 0 times 5 is going to be 0. So I call this a finger trip because that literally means that in standard form, you can just basically make that go away, right? So if I want to know the y-intercept of this equation, all I have to do is say, okay, I'm going to ignore this x, go away. 4 times what gives me 60? Just do 60 divided by 4, basically. Okay, if I do 60 divided by 4, 15, boom, that was our y-intercept. There it is. And then you can do the reverse of that for the x. If I want the x-intercept, I'm going to cover this guy up, and I'm going to do 60 divided by 5, or in other words, 5 times what gives me 60, right? 60 divided by 5, which is 12. Ding, 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 ding. There's my x-intercept, done, right? So that's the big idea. It gives you a real quick, easy way of finding two fast points that are easy to graph. So The y-intercept is always at 0, comma, and then your number. So you just set x equal to 0. That basically disappears, and you just do c divided by the coefficient, and that'll be the y-intercept. And then here you do the same for the x. You cover this guy up so that you only have the x term, and then you do c divided by a, okay, the total divided by that coefficient, and that'll give you the x-intercept. So let's practice that so you can see how nice and quick it is. Let's say that on this equation that's in standard form, I want to find the intercepts nice and quick, okay? So let's start with the x-intercept. For the x-intercept, what I'm going to do is just say, all right, well, the x-intercept is going to be where this y term disappears. So all I'm going to do is solve 3x equals 12. Well, to do that, I would just divide 12 by 3, right? So for the x-intercept here, I would do 12 divided by 3, and that would be 4. So our x-intercept for that equation is at 4. Okay, because I would ignore the y term, make it 0 basically, and I would do 12 divided by 3. That's it, and that's your x-intercept. The y-intercept, I would just do the other way around, okay? I would make that 0, that goes away, and I would divide 12 by 4, which gives us 3. So our y-intercept would give us 3 here. Okay, so pause the video, try these next two, and then come back and check your work. And if you're hearing this, hopefully you paused it and you tried it. So for our x-intercept, we covered that up. We do 16 divided by -1, which is just -16. So our x-intercept is -16. For the y-intercept, it's going to be 16 divided by -4, which is -4. So the y-intercept here is -4. Easy peasy. Okay, and again, if you're seeing this, you already paused it, you tried it, and now you're just checking your work. For this one, for our x-intercept, it would be -30 divided by 5, which is -6. So x-intercept is -6. And for the y-intercept is going to be -30 divided by a -2, which is a +15. So the y-intercept is +15. Okay? So hopefully you did well on those. It's really just making the other term 0 and then dividing the total by the coefficient. That'll reveal immediately what those intercepts are. The really good news is when you have two intercepts, then it's just a matter of plotting them on the axes and connecting them. So it makes it a really easy, quick way to graph. So try number 4. Use the same trick right now. Find the x and y intercept first, and then plot those on the x or y axis. Okay, so we're going to find those intercepts the way we just reviewed. We're going to do, let's find the x-intercept first. That means this would be 0, this whole term would go away, and we would just do 24 divided by the -8, and that would reveal the x-intercept. So x-intercept is going to be the 24 divided by the coefficient, -8, and that tells us that we have an x-intercept of -3. And here's the cool part. Now you just plot that point on the x-axis, and you already have a point on your line. Since it's the x-intercept, we know that point would be right here on the x-axis. Let's do the same for the y-intercept. We're going to do 24 divided by 12. This will disappear. It would be 0, and we would just do 24 divided by 12. And when we do 24 divided by 12, that's just 2. So the y-intercept is at 2. That's here on the y-axis. And then all we have to do is connect the points, and boom, we have created this graph of the entire line. That's the line that is modeled by that linear equation. So there's the nice advantage to using standard form to graph. Let's try number 5. For the x-intercept, y will be 0. So So we make that disappear and we just do the total divided by the coefficient. So 4 divided by 2. And in this case, 4 divided by 2 is just 2. That means our x-intercept is at 2. Our line crosses the x-axis at 2. And then for the y-intercept, we're going to just make the x term be 0 and disappear, and just divide the total by that. Well, 4 divided by 1 is still just 4. I can kind of see it right there. So 4 divided by 1 is 4. That means that this line crosses the y-axis at 4. And then you can whip up your line really nice and quick. Now, I usually highly recommend 3 points. This is the exception. Where you're graphing with intercepts, 2 points is just pretty much always plenty. Okay? So that's the benefit, really, or the advantage to standard form. It lets us find the x and y intercept really quickly, put those right on the axes, connect them. Notice I don't just connect the two. This is not connect the dots, right? I don't just connect the points, but I go past them and I put arrows. I will always look for that unless it's a word problem where it doesn't make sense. Okay? All right, let's try number 6. It says use the values below to fill in the equation, and these are typos. I should say A and B. So that's basically a standard form equation. So that x-intercept of the graph is -10 and the y-intercept of the graph is 5. So we're looking to see which of these might work for that. It's kind of like a multiple choice question. So this is what I'm going to rewrite it because those boxes didn't print. So this is what's going on. We have ax plus by equals 30. And I want to find out what would a and b have to be so that we get these intercepts. Well, remember, on the other side of this, we have a nice little formula that guides us, right? We know that for the y-intercept, this becomes 0. We can always find the y-intercept by doing c over b, the total divided by the coefficient, and the x, the total divided by that coefficient. So that's on the previous page. I'm going to use that to my advantage here. So if I understand that, then I realize, okay, the x-intercept has to be equal to 30 over whatever a is, okay? And I know that x-intercept, I want it to end up being -10. So they want the x-intercept of the graph to be -10. So whatever 30 divided by a is ended up being -10. Can I work backwards and solve for a? Absolutely, right? So we can solve this by just saying 30 divided by what gives us -10, or in other words, multiply by a on both sides. And we get 30 equals -10a, and then divide both sides by -10. And it turns out that a would have to be 30 divided by -10, which is -3. Is that one of our options? Yep, right here. Okay, so a would have to be -3 for us to have an x-intercept of -10, because 30 divided by -3 would give us -10. Let's do the same for the y-intercept. Okay, I know the y-intercept is going to be this total divided by that coefficient, so 30 divided by b, and they told us the y-intercept of the graph is 5, so that comes out to 5. So again, 30 divided by what gives us 5 is a question. And if you don't know, if you know it off the top of your head, well then kudos. If not, you can always solve it by moving the b out of the denominator and then solving for b. And you should see, oh, b is going to be 6. That would be the only number here that when I divide 30 by that number, I would end up with an intercept of 5. That means that b would have to be 6. So really our equation, right, the standard form of this equation would be -3x plus 6y is equal to 30. I know this is not in proper format because that a is negative, but I don't think they were focused on that in this particular example. It was really just about finding the missing values that made these intercepts true. Okay? All right. So hopefully that gives you a nice little introduction to this good old standard form of an equation and why we like to use it to graph, because it gives us those intercepts. Those intercepts are usually important points in real world problems. They're usually like the maximum of each thing that you can have. If I buy all turkey sandwiches or all veggie sandwiches, right? Or if, situations like that, or if I make all adult tickets or just all student tickets is what I sold. So they usually have special meaning, those intercepts, and they also make it very easy and quick to graph, right? All right, so the last thing I want to focus on is the special cases, the vertical and horizontal lines, okay? So these equations are technically actually in standard form. They're just a little bit different. So the horizontal line is the flat one. I always think of that because horizontal has that bar, like the H in horizontal has this line in it. So I always remember, okay, that's got to be the horizontal because I remember it has that line, that flat line going across. The graph of y equals b is always a horizontal line. So if you just see something like y equals 9, y equals -3, and you don't see an x term, that is a horizontal line, okay? And whatever the y-intercept is, that's what you're going to see in the equation. So if the y-intercept is at 5, then it's y equals 5. It will never have an x-intercept because it's parallel to the x-axis, so it's never going to intersect the x-axis, okay? For a vertical line, this is always that pesky one, right? That's the only line in this entire world that will name x equals. And it's because it doesn't have a y-intercept. It's parallel to the y-axis. That's why it doesn't fit into y equals mx plus b either, because it has no y-intercept, it has no slope. It kind of defies all of these laws and rules that we have. This is kind of the exception to everything. So we call this, or we name it by the x equals, and then its x-intercept. That's a vertical line. Okay, so the graph of x equals a being the x-intercept, is a vertical line, and it will pass through that x-intercept that we see in the equation. So if I see x equals 2, that tells me it's a vertical line that passes through x equals 2 and is perfectly vertical and parallel to the y-axis. Okay, so that's the equation of a vertical line. So let's practice that. Okay, if we see y equals 3, then that's immediately, and I say y equals, I don't see an x term, I right away know that's going to be a flat horizontal line, and it's going to have a y-intercept at 3 and no x-intercept at all because it is parallel to that x-axis. So it's going to go straight across right here like that. Okay, and it would have that y-intercept at 3. It would be just a nice horizontal line. This is the equation of that horizontal line, and it shows me the x-intercept, the y-intercept, but it has no x-intercept because it doesn't intersect the x-axis. If I see x equals a number, ding, 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 this is the only time you'll see x equals is when it's a vertical line. So this vertical line is at -1.5. So that's telling me the x-intercept, -1.5, is right about right there between -1 and -2. And this is going to be a perfectly vertical up and down line, like that. And that would be the line x equals -1.5. And that's it. That would be your vertical line. And your horizontal line is just y equals a number or x equals a number. And that's still considered standard form.